This is a re-recorded version of my presentation given at the SAP Inside Track Berlin on September 2nd, 2017. Apparently, there were some kind of audio issues during two of the sessions, one of them being mine. So instead of simply dropping the slides off somewhere and leaving you with an incomplete presentation, here is a recording of the slides with voiceover. Many thanks nonetheless for Oliver and the entire team for organizing the event. I'm looking forward to seeing everyone again next year. As you might have guessed from the title, this talk is partially about creative reuse, some might say abuse, of existing tools. Since circle diagrams are abused frequently and generally frowned upon for good reasons, here is a new mode of abuse as an agenda, because as Vitali said in his talk, every presentation given in Germany needs an agenda, right? As a short introduction, I'm a developer and have spent almost all of my working career in the healthcare, or more specifically hospital environment, about half of the time on the customer side, half of it as a software and solutions supplier, either working for a dedicated service provider or as an in-house consultant and developer. I first come into contact with SAP-based solutions in 2001. My current employer, Extension, is an Austrian company with subsidiaries in Switzerland and Germany. We're a full-stack IT solutions provider for healthcare service providers with a strong focus on application integration. My team and I are focusing on providing additional applications and developing customer-specific solutions for SAP-based healthcare applications. This presentation is an overview of a customer project conducted in late 2015 and early 2016 at the Klinikum St. Georg Leipzig. The in-house service provider St. Georg IT Gesellschaft is responsible for the operation of the entire IT landscape of the central hospital and a number of off-site locations shown here. The central hospital, with more than 1,000 inpatient beds, treating more than 40,000 inpatient and more than 90,000 outpatient cases a year, is among the larger hospitals in Germany. This is an impression of a hospital ward about 150 years ago. Modern-day hospitals look quite different naturally, and even if you don't usually see it as a prominent feature, healthcare IT is vitally important to the operation of any modern hospital. By this, I'm not referring to the computerized devices used in virtually every kind of treatment and examination, and I'm not talking about the current hype subjects like genomics, proteomics, big datomics, and machine learningomics either. Our focus is day-to-day operations of a patient treatment facility, all the stuff that you need to keep the lights on and treat the patients. Indeed, if you were to switch off the central hospital IT systems, you would be in a situation even worse than the one depicted here. In today's hospital, you have much less nursing and auxiliary staff than you had even a few decades back, so sustaining manual fallback procedures over an extended period of time would prove very difficult due to the lack of personnel. Few people know that SAP has a dedicated solution for hospital applications. The Industry Solution Healthcare, ISH, also known as SAP for Healthcare, goes back a long way into time when the system was still called R3. It provides the basic means to manage patients and record the data required for billing and legal statistics, and is mostly used by administrative personnel. The current version is integrated into the enterprise core components, and that is what this talk will focus on. There's a new and improved successor product being developed at the moment, but that has yet to find its way into the day-to-day operations. In addition to ISH, there is a clinical system named ISH Med that provides additional functionality required by the clinical staff. Things like scheduling appointments, documenting findings, keeping track of tasks, accessing medical records, and so on. From a licensing point of view, this is a third-party application that through a series of mergers and acquisitions now is provided by Cerner. From a development standpoint, this application is peculiar in that it is developed in very tight cooperation with ISH on the SAP development systems and delivered alongside ISH. In fact, ISH and ISH Med share parts of their data structures, code base, and function library. ISH Med is currently undergoing a redesign as well, triggered by the changes in the ISH world. But again, this is not overly relevant for this talk. I don't have exact numbers on ISH, but ISH Med is currently being used by about 500 customers in about 32 countries worldwide. Service announcement: when I'm talking fast, my pronunciation of ISH tends to degenerate to ISH, which is not what I'll be focusing on. One of the central applications of both ISH and ISH Med is the clinical workplace. It's an operational application that displays data relevant for a certain situation and allows the execution of any number of actions based on the data displayed. It acts as a kind of navigational gateway to many other functions. In this case, you can see a list of patients occupying wards with some data and indicators displayed next to it and a number of functions overhead. The clinical workplace is used by virtually every physician and nurse numerous times throughout the course of a day, making it one of the most important applications in the hospital environment. The clinical workplace is configured by the administrators that provide workplaces and views. It is very flexible and highly extensible. It allows for the addition of custom functions to the toolbar as well as custom columns to the list display. When defining a view, the administrator chooses a view type that basically specifies what kind of entities are displayed in the view. The view definition also holds the selection criteria, a layout setting for the mostly disk-based display, and a definition of the toolbar functions available above the display. The user is then able to personalize the application again by adding, hiding, and rearranging the list columns. IT applications with a mostly administration-based background are usually regarded as a burden rather than enablement by clinical staff. This is perhaps most aptly reflected by the observation that in just about every hospital you find one or more senior physicians willing to use these mechanical tally counters to record the number of mouse clicks made in a single day and write long complaints about how much time is wasted that way. But aside from the humorous value of that, it pays off to listen to the users. In this case, we were getting rather unspecific complaints about this system being slow. In some rare cases, IT staff was able to witness the slow functions, but not enough data was gathered to reproduce the issue. At the same time, no abnormalities were visible in the underlying system diagnostics, so the performance issues had to be located at application level. An additional complication was a kind of observation bias. When the user clicks a button and then has to wait for a number of seconds, the user will notice that delay and complain to the IT department about that. The preparation and display of a list, on the other hand, is not perceived as an action. The user will rarely comment on the list processing being noticeably slower. This gets even more relevant when you take into consideration that after processing a function triggered from the clinical workplace, the list view is refreshed, and from a user's point of view, the time taken to rebuild the list is perceived as part of the function processing. For these reasons, qualified and actionable performance complaints about the clinical workplace are rare. A side aspect of the entire project was that we wanted to be able to observe the performance behavior of the clinical workplace over an extended period of time. The clinical workplace is a very dynamic application that is extended and reconfigured very frequently because of business and workflow changes. This can lead to performance degradations being introduced unintentionally. Identifying these issues and determining the exact date when the changes were introduced helps a lot in tracking down the actual cause and fixing it. Now, unspecific complaints are not suitable for further immediate action. We needed to gather objective data through measurements and continuous monitoring. In this presentation, I'll focus on the clinical workplace list preparation and display. The techniques and tools used are applicable to many other applications as well. We used mostly existing tools, eCATT with some additional components for logging, some external tools for evaluation and report generation, and then the built-in runtime analysis SAT to track down the individual issues. When taking runtime measurements of the clinical workplace, it was immediately obvious that taking a measurement of the entire view was necessary, but not that valuable on its own. If you want to identify which display routine is responsible for a slow list update, it is necessary to measure each column individually. The reason for this is that most of the data providers have a built-in logic that will only populate the display fields when they are actually visible. Measuring each column in isolation helped a lot to track down the implementations responsible for the worst performance issues. Another aspect that was very clear right from the start was that we needed to get the scope and the environment for the measurements right. On one hand, the flexibility and versatility of the clinical workplace make it impossible to measure all possible combinations. Then, we're faced with a dataset that is constantly changing and grows stale very fast. A copy of the production system will exhibit a totally different system behavior after only a few days, because many of the business processes happen on much smaller timescales. Also, measuring the performance on a separate system will usually not lead to the same performance characteristics due to different hardware settings and missing concurrent user access. For discussions with the users, you need to have credible measurement results with values that the users can relate to. So we decided to take the measurements in the production environment using the actual user settings, albeit without taking the personalizations into account. Even then, the number of assigned views was too great to allow for a continuous observation of all views, so we had to restrict the selection further. In order to do so, we dug out an old addition to ISH that records every call of a view in the STAD Workload Statistics. We found that the standard implementation was missing an important key value and had to enhance the logging slightly. Details can be found in this blog post. By evaluating the data gathered through the workload statistics, you get this heartbeat of the system. It gives a nice impression of the actual system usage down to the common lunch break times. More important to the subsequent project was this ranking of workplace and view combinations by the number of calls. In this case, 2 nursing views are at the top of the list because the nursing staff uses a standardized view throughout the entire hospital, while the physicians have views tailored to the needs of the individual departments. With this data, we knew where to look. The next step was finding out how to look. This is an overview of the eCATT and testing workbench objects involved in the process. We're starting with 4 basic eCATT objects. eCATT is able to execute tests on multiple systems and gather the data. The target systems are defined in a system data object. Since we only had one target system, I won't be showing the system data here, and I won't be going into the start profile either, since we used mostly default values here. The next slides will feature the test script and the test data containers that define the actual testing procedure and the data used to execute the tests. These objects are assembled into a test configuration that is then added to a test catalog and subsequently to a test package with a test plan. A regular system job then triggers a less known feature called the Foreground Scheduler that executes the tests. These are the transaction codes used to define and edit the objects displayed here. If you want to do this yourself, be sure to assign the software components to the objects consistently, because it will be unnecessarily hard to locate the objects later on if you don't. This is one of the test scripts used. It basically prepares the user-specific settings and determines which technical screen object has to be selected to display the view. It then calls the view once to ensure all system-level buffers are filled before iterating through the fields of the list, preparing a user variant to isolate each field, and determine the runtime used to display the field. This script uses an auxiliary class that provides the customizing evaluation and manipulation functions, as well as a basic stopwatch functionality. The actual UI calls look intimidating, but are mostly recorded and then adapted manually. The script has a set of importing parameters shown here that will be filled with the keys of the workplace and the view combinations to be tested later on. These keys are used to define the structure of the test data containers. First, the parameters are defined and assigned a type description. On the second page, these parameters then become the attribute columns of the test variants. This setting allows for the use of the same test data for multiple test scripts. The workplace and view combinations shown here are basically the most used combinations determined through the workload statistics shown earlier. The test configuration then combines these objects and states which test script should be run on what system with which start profile and using whatever test data. It allows for an additional selection of the variants to be executed. This test configuration could now be run manually, but that essentially blocks the machines where the test is run. To run the tests automatically, some additional measures are required. For that we need to use the test workbench. I won't be going into the details, because that would be enough material for another talk, but just show the few objects that we needed. First, we had to define a test catalog and add the test configurations. Here it is important to specify the variants to be used correctly. Then we created a test plan, and here you can see why it is important to use the correct software components. From the test plan, a test package was created. The details screen would allow for a manual scheduling of the test package, but we wanted to run the test repeatedly without user intervention. For this, we used the program named here, scheduled as a normal background job. Be aware that this program is slightly unusual to handle. For instance, you need to use the value help to populate some inactive parameters. This program generates job definitions that are then picked up by the Foreground Scheduler. The Foreground Scheduler is a normal Dynpro-based application that, when registered and active, periodically refreshes itself to check for new jobs. Once a new job is found, it then starts the eCATT test scripts as specified earlier. This is run on a special virtual machine emulating a user desktop set aside specifically for these tests. This is what the testing machine looks like. You can see the Foreground Scheduler waiting for a new job. Once the job is picked up, it's started immediately and the clinical workplace is started in a new window. In this case, a document view is being tested. The system first calls the entire document list with default settings to prepare the system buffers, then restarts the clinical workplace. Now the view is shown with just the patient number isolated. The document key fields are left in there for technical reasons. Then the clinical workplace is started again and the view is shown with only the case number column, and so on. These test sets are run several times a day, every day. What you get as a result are tables like these: date and time of the test run, the workplace and view ID under test, and either the total runtime or the runtime with an isolated column. This has to be recorded in a custom table, since this data is not easily available from the eCATT log. Now we have the usage statistics, shown earlier, and the performance measurement results. We also need some information about the system environment, like the descriptions of the views and workplaces, or the names and types of the columns. This data then needs to be pre-processed and evaluated to produce some meaningful reports. At the time, there was no BI solution present in the customer system landscape, so we used an old open-sourced version of RapidMiner. RapidMiner is usually known for data mining and machine learning tasks, but we did not use any of these functions, as you will see in a moment. This is what the RapidMiner IDE looks like. You basically design processes by choosing building blocks, so-called operators, and modeling the data flow between these operators that you can choose from an extensive library. Each operator comes with an inline description of its functions and settings. Most operators have parameters that can be set. The entire process as well as most of the data files are stored in a repository. The processes have input and output elements that can be connected to files in the repository or connected directly when the process is embedded in another process. This is an example of an input process. The process can also be shown as a tree display, which shows the full names but doesn't let you see the data flow anymore. In this case, we read a CSV file, then filter out some invalid sets that somehow made it into the data file. We then perform a few type conversions to make the data handling easier later on. Another cleanup operation that happens at this stage is to mitigate the effects of a refactoring project that took place while the measurements were already running. We essentially had to map corresponding workplace keys in order to keep the performance history. The data imported through these steps is then stored and used for the subsequent steps. This is one of the processes that combines and prepares the data for evaluation. It consists of two sub-processes. The first one combines the performance data and the customizing information that contains the workplace and view names. This operates similar to a database join, but without any underlying database structure. You can simply combine two datasets read in from CSV files or any other data source. The combined data is then split into two streams for the entire views and individual columns respectively, and the column-related data is again combined with the column definitions to provide the human-readable names. The second sub-process attempts to match the isolated column runtimes with the total runtime of the view. Since the tests might be run several minutes apart, comparing these values will always lead to a certain fuzziness of the results, but since the data is used only as an indication what to investigate in detail, that is within acceptable limits. This is one of the report generating processes. I won't go too much into the details here. It basically opens a report based on a custom template, adds a fixed text information, and then iterates through all view types measured and adds a section header for the view type. Below that, two sets of graph and table are added, with the first one being sorted by runtime, the second one alphabetically. This is what the generated report looks like with the fixed text, the section heading, the graph and the top of the table. And this is one of the graphs in detail. The interesting observation here is not so much the wide range of runtimes between the topmost and the bottommost view. That is unsurprising, since the first view is a small ICU at a remote location, while the last view is a hospital-wide view of the largest department of the hospital. What is more interesting is A, the runtime difference between various views supplied for departments roughly of the same size, and B, the yellow and red dots showing views with widely varying runtimes. Both of these warranted further investigation. This table combines the usage and performance data and shows the average runtime of the most used views. It also gives some kind of perspective to the entire performance optimization project. If, for example, the runtime of this department level view could be reduced from 12 to about 4 seconds, we would be able to return about half an hour per working day to the physicians of that department. And initial performance improvements in that order of magnitude were indeed possible, as you will see in a moment. This graph shows the development of the runtime of one particular view over time. This graph shows a very peculiar sawtooth pattern with gaps between each peak and the start of the next series. It was at the beginning of the project when we noticed that the SAP GUI kept on disappearing from the front-end machine. When connecting to the machine, it was sitting idly on the desktop with all GUI windows gone. It took us a moment to figure out what happened. Apparently, we triggered some kind of memory leak in the GUI that led to an increasing runtime throughout the tests, until at some point the shared memory management system ran into some issue and shut down the entire application. Unfortunately, that is one of the issues that we were unable to resolve even after months of communication with SAP support. In the end, we resorted to restarting the entire machine before every test run. Unfortunately, you can see that in this case the disturbance by the memory leak is about 3 times as large as the performance of the view we're trying to measure. That's noise to signal ratio, not signal to noise ratio. But we were able to get some information from the early measurements nonetheless. This is a similar graph with a different timescale. Despite the huge noise level, you can still see a drop in the runtime of this view to about a third of its initial value, and that's not an artifact, that's an actual performance improvement that we were able to effect after we knew where to look. In order to identify the issues in detail, we used the standard runtime analysis transaction in SAT, mostly the profile overview and the hit list to identify the most time-consuming actions. In this particular application, we used a filter during the trace to cut out all the framework programs that were of no interest to the actual runtime of the view. From the original set of findings, I've selected 3 examples of actual findings. Let's see what the actual issues looked like. This is an example of a data selection that took about 1.5 seconds for a certain view. We traced that back to a function that calculates the age of a patient. In the hospital environment, you usually need to know the age of the patient at admission because you need a stable value. In this example, a standard function module was used to determine the age. When tracing the SQL statements in question, we noticed a very particular pattern. The first line, the case number ending with 902 is queried. In the second line, 902 and 798. In the third line, 902, 798 and 303, and so on. This is reminiscent of a German children's game, Ich packe meinen Koffer. As you can see here, at a certain point the where clause gets too big so that the query is split up into 2 statements that are run sequentially and then merged again. This is the typical behavior of a for all entries in statement going berserk. Here is the code in question. To cut right to the point, in line 30 a function module is used that fills a buffer with the movements of any number of cases specified, which is not really necessary here, since the entire function module only takes one single case number, see line 5. To call the movement selection module, a global internal table is used, and that table cannot easily be emptied again. Therefore, the table, and with it the resulting select statement, keeps on growing. Now in my book, that's a bug that should be fixed. Turns out that in the SAP book, this is an unreleased function module that we should not have used. Right. One important takeaway besides this very helpful information though, this is a bug that we will only be able to observe with a sufficiently large testing dataset. If the view only ever contains 5 or 10 patients, the increased runtime will not be prominent enough to warrant further investigation. The second example is a classic performance trap that we found in customer extension. If you're a developer yourself, better fasten your seatbelts. The program initially came under investigation for some redundant data selection, but in the code we found these 2 statements. Now, apart from the unnecessary loop form, this will not look too bad to most developers, until I show you the table definitions. In both cases, the developer neglected to add primary key fields to the where clause, even though the values in question were present at runtime. In this case, we were able to improve the runtime of the entire view by about 2.5 seconds, simply by adding the 2 key fields to the select statements. Sometimes it is small oversights and sloppy programming like this that can drag down the performance and reputation of the system. The third example is more complex. This is a graph for a single view that shows the columns on the left side and a rough comparison between the runtime of the total view and the runtime of the isolated column. This graph gives an impression of the fields that contribute the most to the overall runtime of the view. Unexpectedly, it turned out that the patient name and birth date were rather expensive to display. Investigating this, we found out that for about 250 patients in the list, about 1,750 address data fetch operations were required. The reason for this is a bit more involved. Historically, the patient master data was not normalized to a degree that would seem appropriate today. It contains address data of the patient, next of kin, employer, and other persons or entities. A secondary set of address data tables was introduced at a later point in time, but the then redundant address fields in the patient data were kept in sync because removal was not feasible for maintenance reasons. Recently, the address data structure had to be changed due to legal requirements, but that structural change was not applied to the patient data, so that it now became impossible to keep the redundant fields in the patient data in sync with the address data. That means that as soon as the additional fields are used, the patient data has to be updated from the address data on read access. In this case, it's even worse. The address data is irrelevant because it is not part of the list display and thus cannot be used. But since the patient data access is buried 2 levels deep inside a generic function, that information is not available and the address data is read and processed for every single patient. Unfortunately, that is one performance issue that is unlikely to be resolved. It is simply part of the legacy of ISH and ISH Med that customers will have to live with. Coming to a conclusion. As an overall conclusion, one might say that the general approach is definitely viable. It is possible to establish a continuous performance monitoring system using mostly stock tools, and while the entire process is rather time-consuming, the performance improvements we were able to achieve were definitely appreciated. eCATT with the Foreground Scheduler proved to be a valuable toolkit, although it was a pain you know where to set up. As a developer, you might take a look at the eCATT documentation and be tempted to think, this is just one step beyond basic, that shouldn't take too long. Wrong. It certainly does not involve any magic, but both the technical approach and the tools like the eCATT script editor contain quite a few pitfalls that in the end lead to a much more extensive learning experience than we would have anticipated. In the end, though, we got valuable results, and that's what counts. One important aspect is that while the automation might seem very costly to set up, it does pay off in the long run. We would not have been able to implement and verify the actual performance improvements without the large-scale measurements. RapidMiner proved to be a great tool for this task, albeit being completely over-engineered for this use case. It is very easy to learn and rather well documented, and it lends itself very well to an iterative approach where you won't be able to define the kind of reports that you need for a detailed analysis up front. The downside is that, unless you're using the very outdated open source variant, it can be a very costly tool, and it has a very dynamic licensing scheme. One might get the impression that it changes with every major release. SAT should be known to every developer, and that are exactly its 2 major problems. It should be known, but apparently it isn't, and it requires a developer mindset, as well as knowledge about the application being examined. The latter is required to spot irregularities like redundant data access. Furthermore, SAT is virtually useless for large-scale performance optimizations, because detailed traces of an entire application, like the clinical workplace, get too big to handle. However, once you have narrowed down the performance issues to some areas that might be worth investigation, this is the tool of choice. The overall reception of the project was very good. Except for the SAP GUI memory leak, contact with SAP and Cerner product support was very positive, not least of all because we were tracking down product issues that can only be identified with customer system in active use. There are likely hundreds of similar suboptimal constructs we found throughout the codebase, but through our research we were able to identify the ones that were actually responsible for performance issues and therefore worth fixing. On the same note, a rather small set of fixes throughout the customer coding were sufficient to provide a vastly improved user experience. Again, going through the entire customer codebase of a system that has been in use for more than 10 years would not have been practical. One important lesson of this project was that it is relatively easy to reap the low-hanging fruits through initial performance improvements, but it is hard to keep the project going once these improvements are made. The maintenance of the test infrastructure and the test cases takes time, as does the communication on long-running messages. You also need to be aware that with this project, you're effectively pointing at your fellow developers and telling them to clean up that particularly nasty smelling bit of code, and not everyone can appreciate that as constructive criticism. On the other hand, a project of this size with the initial investments is probably too large to only take the initial improvements and then shut it down again. That concludes the presentation. As far as I can remember, there were 2 questions from the audience. Did the continuous performance measurement itself have an influence on the system load? Answer: there was no noticeable effect. Remember that the storage, operating system, database and network statistics were all green, so we were confident that the system still had enough headroom to tackle the additional load of the tests. The problem was not a lack of system resources in the first place, but rather that the system was performing nonsensical operations at top speed in the first place. Second question: did the project results have an impact on the development methodologies used, for instance unit testing? Answer: the problem with the clinical workplace is that due to its integrative and data-centric nature and its historically grown structure, it does not lend itself very well to these techniques. You can't mock the entire framework consistently, and if you could, it would be a rather large effort without any guarantee to actually identify the performance issues in a non-production environment. So with this, I'd like to end the re-presentation of my SAP Inside Track session. Thanks to everyone involved in the preparations and organization. Thanks to all the visitors, and thank you for your interest. Have a nice day.